grounding electrode conductor, or GEC, must be sized based on the size of the service entrance conductors as per the National Electrical Code Section 250.66. This requirement exists because the GEC is responsible for carrying fault currents back to the power source, and its size must be proportionate to the amount of current that can potentially flow during a fault condition. Now let's consider the critical equipment earthing conductor, or CEE. The CEE serves as a supplemental grounding electrode and is only mandated under specific circumstances, such as for grounding critical medical equipment, often abbreviated as CME. According to the National Electrical Code Section 517.140b, the CEE must be a minimum of a number 4 American wire gauge, often written as AWG, insulated copper conductor. The relatively smaller size of the CEE compared to the GEC reflects its different role and the amount of fault current it is expected to handle. The primary function of the GEC is to establish a low impedance path for fault currents to return to the power source. This low impedance path is crucial in preventing dangerous voltages from developing on the electrical system during a fault. Consequently, the size of the GEC must be adequate to handle the potential fault current that could flow through it. The CEE, on the other hand, has a more limited role. It is specifically employed for grounding critical medical equipment to ensure patient safety in the event of a failure or compromise of the normal grounding system. Since the fault current that the CEE is likely to carry is much smaller compared to the GEC, the conductor size requirement is correspondingly less stringent. In summary, the GEC is sized to effectively manage fault currents, providing a robust path for current to return to the source during a fault. In contrast, the CEE is sized to provide a supplemental grounding path specifically for certain critical equipment. This difference in their intended function directly dictates their respective sizing requirements as outlined in the National Electrical Code. Firstly, let's delve deeper into the sizing requirements for the grounding electrode conductor, the GEC, as dictated by the National Electrical Code, specifically Section 250.66. The primary purpose of the GEC is to connect the electrical system's grounded conductor, typically a neutral, to a grounding electrode, such as a ground rod, a metal underground water pipe, or a concrete encased electrode, also known as a U for ground. This connection establishes a reference point at or near 0 volts potential, which is crucial for safety and proper operation of the electrical system. The size of the GEC is not arbitrarily chosen. It is directly correlated to the size of the service entrance conductors. Service entrance conductors are the conductors that bring power from the utility company's transformer to the building's main service disconnect. The National Electrical Code Table 250.66 provides guidance on selecting the appropriate GEC size based on the size of the service entrance conductors. For example, if the service entrance conductors are number 2 American wire gauge copper or number 1/0 American wire gauge aluminum, the GEC is required to be a minimum of number 8 American wire gauge copper. As the size of the service entrance conductors increases, the required size of the GEC also increases. This correlation is essential because the GEC must be capable of safely carrying the maximum ground fault current that could potentially flow through it. Ground fault current is the current that flows through the grounding path when a fault occurs, such as when a live conductor comes into contact with a grounded metal part. Secondly, let's shift our focus to the critical equipment earthing conductor, the CEE, and its specific application in healthcare facilities, particularly in relation to critical medical equipment. The National Electrical Code Section 517 addresses the requirements for healthcare facilities to ensure patient safety. Within this section, 517.140b specifically addresses the requirements for the CEE. The CEE is a supplemental grounding conductor that is used to ground critical medical equipment. Critical medical equipment is defined as equipment that is essential for patient care and whose failure could result in serious injury or death. Examples of critical medical equipment include life support systems, heart monitors, and surgical equipment. The CEE is required to be a minimum of number 4 American wire gauge insulated copper conductor. This requirement is intended to ensure that the CEE is capable of providing a low impedance path for fault current to flow back to the source in the event of a ground fault. The CEE is connected to the equipment grounding bus in the patient care area and then routed back to the main electrical panel. This provides a redundant grounding path for the critical medical equipment, minimizing the risk of electrical shock to patients and healthcare personnel. The CEE is not intended to be the primary grounding path for the critical medical equipment, but rather a supplemental path in case the normal grounding path fails. The normal grounding path is typically provided by the equipment grounding conductor that is run with the branch circuit supplying power to the equipment. The CEE is intended to provide an additional layer of safety to ensure that the critical medical equipment is properly grounded. Thirdly, let's consider the reasons why the sizing requirements for the GEC and CEE differ so significantly. The primary reason lies in their differing roles and the magnitude of fault current they are expected to carry. The GEC is part of the overall building grounding system and is designed to handle large fault currents that can occur during a ground fault on any part of the electrical system. It is sized based on the service entrance conductors to ensure that it can safely carry the maximum potential fault current. The CEE, in contrast, is a supplemental grounding conductor that is specifically used for critical medical equipment. It is not intended to handle large fault currents, but rather to provide a redundant grounding path in case the normal grounding path fails. As a result, it can be smaller in size than the GEC. Another important factor to consider is the impedance of the grounding path. Impedance is the opposition to the flow of alternating current. A low impedance grounding path is essential for ensuring that fault current can flow quickly and safely back to the source. The GEC is typically connected to a grounding electrode system such as a ground rod or a metal water pipe, which provides a low impedance path to ground. The CEE is also connected to the equipment grounding bus, which is connected to the grounding electrode system. This ensures that the CEE also has a lower impedance path to ground. The National Electrical Code provides detailed requirements for the installation of grounding electrode systems to ensure that they provide a low impedance path to ground. This includes requirements for the size and type of grounding electrodes, as well as the methods for connecting them to the grounding system. Fourthly, it is crucial to understand the consequences of improperly sized grounding conductors. If the GEC is undersized, it may not be able to safely carry the fault current during a ground fault. This can result in the conductor overheating and potentially melting, which could lead to a fire or an explosion. Additionally, an undersized GEC may not provide a low enough impedance path to ground, which could result in dangerous voltages developing on the electrical system. These voltages could pose a shock hazard to people who come into contact with grounded metal parts. If the CEE is undersized, it may not be able to provide a redundant grounding path in case the normal grounding path fails. This could result in the critical medical equipment becoming ungrounded, which could pose a shock hazard to patients and healthcare personnel. It is therefore essential to carefully follow the National Electrical Code requirements for size and grounding conductors to ensure the safety of the electrical system. Fifthly, the concept of impedance deserves further clarification. Impedance, in the context of alternating current circuits, is the total opposition that a circuit presents to the flow of current. It is analogous to resistance in a direct current circuit, but it also includes the effects of capacitance and inductance. A low impedance grounding path is crucial for effective grounding because it allows fault current to flow quickly and easily back to the source. This rapid flow of fault current is necessary to trip the circuit breaker or fuse protecting the circuit, which will interrupt the flow of current and prevent damage or injury. The impedance of a grounding path is determined by several factors, including the length and size of the grounding conductors, the type of grounding electrodes used, and the connections between the grounding conductors and electrodes. To minimize impedance, grounding conductors should be as short and straight as possible. Grounding electrodes should be of a type that provides good contact with the earth, and connections should be made using approved methods and materials. Sixthly, consider the role of the equipment grounding conductor, often abbreviated as EGC, in relation to both the GEC and the CEE. The equipment grounding conductor is a critical safety component of the branch circuit that supplies power to electrical equipment. Its purpose is to provide a low impedance path for fault current to flow back to the source in the event of a ground fault within the equipment. The EGC is typically a wire that is run along with the circuit conductors inside the conduit or cable. It is connected to the metal enclosure of the equipment and to the grounding bus in the electrical panel. In the event of a ground fault, the fault current will flow through the EGC back to the grounding bus, where it will then flow through the GEC to the grounding electrode system. The EGC is sized according to the size of the circuit conductors, as specified in the National Electrical Code Table 250.122. It is important to ensure that the EGC is properly sized and installed to provide an effective grounding path. In the case of critical medical equipment, the CEE provides a supplemental grounding path in addition to the EGC. The CEE is connected to the equipment grounding bus and then routed back to the main electrical panel, providing a redundant grounding path in case the EGC fails. Seventhly, let's discuss the specific types of grounding electrodes that are commonly used in electrical systems. Grounding electrodes are conductive objects that are buried in the earth and connected to the grounding system. Their purpose is to provide a low impedance path to ground, allowing fault current to flow safely back to the source. There are several different types of grounding electrodes that are recognized by the National Electrical Code. These include metal underground water pipes, concrete encased electrodes, ground rings, and ground rods. Metal underground water pipes are often used as grounding electrodes because they provide a large surface area in contact with the earth. However, they must be electrically continuous and free from insulating joints or cuttings. Concrete encased electrodes, also known as UFA grounds, are made by encasing a length of bare copper conductor in concrete. They are often used in new construction because they can be easily installed during the pouring of the foundation. Ground rings are made by burying a bare copper conductor in a circle around the building. They are typically used in areas with poor soil conductivity. Ground rods are made by driving a metal rod into the earth. They are a simple and cost-effective grounding electrode. The National Electrical Code specifies the minimum size and length of grounding electrodes, as well as the methods for installing them. It is important to follow these requirements to ensure that the grounding electrode system provides an effective grounding path. Eighthly, it's important to note that the requirements for grounding and bonding can vary depending on the specific application and the type of electrical system. For example, the requirements for grounding in healthcare facilities are more stringent than those for general commercial or residential applications. This is because healthcare facilities contain sensitive medical equipment that can be affected by electrical noise and interference. Additionally, patients in healthcare facilities are often more vulnerable to electrical shock. The National Electrical Code Section 517 provides detailed requirements for grounding and bonding in healthcare facilities. These requirements address issues such as the use of isolated power systems, equipotential grounding, and the installation of CEE. It is important for electrical contractors and engineers who work in healthcare facilities to be familiar with these requirements. Similarly, the requirements for grounding in industrial facilities can be different from those for commercial or residential applications. Industrial facilities often contain large motors, generators, and other equipment that can generate significant electrical noise and interference. Additionally, industrial facilities may have hazardous locations where flammable gases or vapors are present. The National Electrical Code provides specific requirements for grounding in these types of facilities. Ninthly, let's address the concept of bonding in electrical systems. Bonding is the process of connecting together all of the metal parts of an electrical system to create a low impedance path for fault current to flow back to the source. This includes metal conduits, metal enclosures, metal raceways, and metal equipment housings. Bonding is essential for preventing dangerous voltages from developing on these metal parts during a ground fault. If a metal part is not properly bonded, it can become energized with a voltage that is high enough to cause an electrical shock. The National Electrical Code requires that all metal parts of an electrical system be bonded together using approved methods and materials. This includes the use of bonding jumpers, bonding bushings, and other bonding devices. The size of the bonding conductors is determined by the size of the circuit conductors, as specified in the National Electrical Code Table 250.102 cone. Tenthly, it is crucial to perform regular inspections and testing of grounding and bonding systems to ensure that they are functioning properly. Grounding and bonding systems can deteriorate over time due to corrosion, loose connections, and other factors. Regular inspections can help to identify these problems before they become serious. Testing of grounding and bonding systems can be performed using a variety of instruments such as ground resistance testers and impedance testers. These instruments can measure the resistance and impedance of the grounding path to ensure that it is within acceptable limits. The National Electrical Code recommends that grounding and bonding systems be inspected and tested at least every 3 years. However, in some cases, more frequent inspections and testing may be necessary. For example, in healthcare facilities, grounding and bonding systems should be inspected and tested annually. By performing regular inspections and testing, it is possible to identify and correct problems with grounding and bonding systems before they can pose a safety hazard. Lastly, it's important to remember that electrical codes and standards, including the National Electrical Code, are constantly evolving to reflect new technologies and best practices. Staying up to date with the latest code requirements is essential for ensuring the safety and reliability of electrical systems. Electrical contractors, engineers, and other professionals who work with electrical systems should make it a priority to attend training courses, read industry publications, and participate in professional organizations to stay informed about the latest developments in the field. By continuously learning and improving their knowledge, they can help to ensure that electrical systems are designed, installed, and maintained in accordance with the highest safety standards. In the realm of electrical safety, understanding the nuances of grounding and bonding, particularly the distinction between the grounding electrode conductor and the critical equipment earthing conductor, is paramount for preventing electrical hazards and ensuring the safe operation of electrical equipment.